let's pick off literally where we left off when my computer died on Tuesday. Thank you. I never know what day of the week it is, so thank you for that. And continue to talk about Y connected loads. So let me get to the appropriate point in my notes here really quick. Go. So it looks like this thing died when I was labeling my line voltages. The last one I have over here is the line voltage VCA. And it should be VBC here. And VCA. And so the next thing that we would be identifying in this particular load would be our phase currents. So it's been a couple of days, so just to remind you, the phase currents are the currents that flow through a single phase of our source or load in this case. So that would be this current flowing into the positive polarity terminal of ZYA. So this is going to be our current IAN. This current flowing into the positive polarity terminal of ZYB. So this would be IBN. And this current flowing into the positive polarity terminal. Thank you so much, Marcia. I'm sorry I forgot and to make you walk out here in this terrible weather. Thank you. On our other representation, here's where IAN is, IBN, and ICN. So these are all of our quantities for our Y connected load. So the last load that we need to look at is then our delta connected load. So this is going to be very similar looking to our delta connected source, except it's going to be full of impedances. So going to look something like this. So let's call this terminal A. Excuse me, this should be a capital A because we're on the load side of the system. This will be our B terminal. Oh, actually, I'm usually referring the load quantities over to the left. A, B, and C, like so. So I'm going to label this particular impedance Z delta A. Between B and C will be Z delta B, and between C and A will be Z delta C. Let's see. My other representation is going to look something like this. Here's terminal A, terminal B, and terminal C. So this would be Z delta A, Z delta B, and Z delta C. All right, so what should our phase voltages be in this system? As a reminder, a phase voltage is the voltage drop over a single phase of our load here. Right, but what is it going to be? Well, what are the labels going to be, right? So we're using a double subscript notation for everything. I disagree. So a double subscript notation means one of our terminals is going to be the positive polarity terminal and one of the other terminals is going to be our negative polarity terminal. So I'm looking for something like VAB, VAC, that kind of thing. So VAB, absolutely. And then VBC. And VCA like so. What about our line voltages? So recall that a line voltage by definition is the voltage drop measured between two transmission line terminals. Exact same thing, right? So VAB, VBC, and VCA. So once again, for a delta connected anything, it seems like our line voltages and our phase voltages represent the exact same quantities. We're going to use that relationship to our benefit a little bit later on. And then the last thing that we need to identify is our phase currents. So these will be the currents flowing into the positive polarity terminals. IAB, IBC, and ICA like so. And this is getting real busy. I'll try to fit it in. So there where our different quantities that we might be interested in for a delta connected load are. Okay, so we have finished the background section. We're now actually ready to throw some math at this thing and see how these three-phase circuits behave. So before I move on to bigger and better things, anybody have any questions about any of the stuff that we've talked about thus far? All I've been trying to do for the past 12 minutes of today and an hour and 10 minutes or whatever of last Tuesday was make it very, very clear as to what the quantities are and what they represent. Because as you'll see in the in-class assignments and all that kind of stuff, I'm not going to say find this thing. I'm going to say find the line currents, find the phase voltages, that kind of thing. And I'm going to expect you to understand what quantities that I'm asking for, which is why I went through the trouble of defining literally every possible quantity that I could be looking for on these figures, right? Okay, so let's move along to balanced three-phase circuit analysis. So we are going to start by looking at a YY system. Okay. So let's say that I have a phase voltage VAN like so. Here's my A terminal. Voltage VBN. Like so. Here's my B terminal. And a voltage VCN like so. This point of interconnection here is my neutral, but I'm going to do something a little bit different here. So in the previous circuit that I drew, we did not use a neutral wire. And in this one, we are going to. So we're going to actually make a connection between the neutral terminals of our source and our load. So on the left-hand side here, I have my Y-connected source. Over here on the right-hand side, I'm going to draw a Y-connected load. So this is going to be ZYA. Here's my capital A terminal. ZYB. Here's my capital B terminal. ZYC. My capital C terminal. And then down here will be my capital N terminal for my neutral connection. And we are going to connect our source to our load using transmission lines. So I'm going to call this impedance ZWA. So it represents the impedance of the A phase of the transmission line. This guy here will be ZWB for the B phase of the transmission line. This guy here will be ZWC. And we are going to assume that our neutral conductor has some impedance as well. So I'm just going to call this ZN. So I want to talk about a couple of things here before we get into the nitty-gritty of things. We are going to be defining what it means for a three-phase system to be balanced. It's a fairly rigorous checklist. And one of those constraints is that the impedance of our transmission line system has to be equal across each phase, except for the neutral, right? So that means the A phase conductor, the B phase conductor, and the C phase conductor all have to have the same impedance, which usually just means it's the same type of wire and it's roughly the same length of wire. For the neutral conductor, though, it can be different. And we're going to see why it can be different very shortly here. But if we were to pull out a National Electronics Code book, there are very specific rules for what the values of the transmission line cables are. And it's a different set of rules for the neutral conductor because the expectation is that the neutral conductor will carry significantly less current. So it can be sized much, much smaller. And we'll see why it carries that current here in a moment. Okay. So we have a three-phase Y-connected source on the left-hand side, a three-phase Y-connected load on the right-hand side, and transmission lines connecting our source to our load. This circuit is considered balanced. Under the following criteria. Okay. So let's start by talking about things on the source side. So our first criteria is that the magnitude of the phase voltages at the source are equal. So this means that the magnitude of the voltage VAN is the exact same thing as the magnitude of the voltage VBN is the exact same thing as the magnitude of the voltage VCN. Okay. So the magnitude of all of our voltages are equal. We can ensure that is the case by buying a well-built generator effectively, right? So as long as the coils that are generating these voltages are of the same type of wire and have the same number of turns, those voltages are going to be equal. That's not something that we actually have any real control over because that's determined at the place that this thing is manufactured at. But they are manufactured such that all those magnitudes are going to be the same. If they're not, your voltage source is literally physically damaged in some way. Okay. So that's our first criteria. Our second criteria is that the phase separation between phase voltages at the source is 120 degrees. So that means the angle of our voltage VAN, let's call it let me rephrase how I'm going to do this. The angle theta BN is exactly equal to theta AN minus 120 degrees, and the angle theta CN is exactly equal to the angle theta AN minus 240 degrees for a positive phase sequence, or theta BN will be theta AN plus 120 degrees, and theta CN will be theta AN plus 240 degrees for a negative phase. So once again, all I'm saying here is that for our source to be balanced, the B phase has to be 120 degrees out of phase with the A phase, and the C phase has to be 120 degrees out of phase with the B phase, okay? So for a positive phase sequence, that means that the B phase lags the A phase by negative 120 degrees, and the C phase lags the B phase by negative 120 degrees. Exactly the same crap that I was talking about on Tuesday, okay? If we put these two constraints together, we could say that if VAN is equal to the magnitude of VAN angle theta AN, then VBN has to be the magnitude of VAN with an angle of theta AN minus 120 degrees, and VCN is simply the magnitude of VAN with an angle of theta AN minus 240 degrees for a positive phase sequence. Meaning that VBN is simply VAN multiplied by 1 angle negative 120 degrees, and VCN is VAN multiplied by 1 angle negative 240 degrees. And once again, these are for a positive phase sequence. Okay. So if I know one of those three voltages, I know all three of those voltages because I can get the other ones simply by shifting by 120 degrees, okay? So I really only need to know one out of those three voltages in order to know all three of them, okay? All right, so this is what it takes for us to have a balanced three-phase source. We are going to assume that every source that we have is going to be a balanced three-phase source because once again, they're manufactured to be balanced. If they are not balanced, there was a problem with the manufacturer. Okay, so we have no control over that whatsoever. So now let's talk about things that we do have control over. So if we want the transmission line portion of this system to be balanced, then we need the transmission line impedances must be equal. So that means ZWA must be the same as ZWB, must be the same as ZWC. So when we have a balanced system, we'll probably just use a shorthand notation of ZW because all of them are supposed to be the same thing in a balanced system. So we no longer need to differentiate the A phase, the B phase, and the C phase because they're all the same damn thing. Okay. So for our transmission line impedances to be equal, we need to be using effectively identical conductors. So same length, same diameter. Not that it particularly matters with regards to impedance, but for safety's sake, probably the same insulation as well. Okay. So generally speaking, this is just a big spool of wire that you cut up into 3 equal lengths. And then that's how you connect, you put lugs on it so that you can connect the things. Okay. On our load side of things, we effectively have the exact same criterion. Okay. For this system to be balanced, the load impedances must be equal, meaning that ZYA has to be the same thing as ZYB, has to be the same thing as ZYC, And so we'll simply call it ZY. So this is really where we have the most amount of control because it depends entirely on what we connect to, right? So you guys within the next couple of years are going to go out into industry and work for various types of companies, some of them being electrical utilities, others being manufacturers and all of that kind of good stuff. What do you think some of the three-phase loads you might see are? Anybody have any thoughts? Nope. Okay. So the two most common ones are motors and HVAC units. A three-phase motor is going to be by definition balanced, much like the source, because it's built to be that way very specifically. Okay, so you don't have any problems to worry about whatsoever there. But for, thank you, for an HVAC unit, it's very likely going to be an unbalanced three-phase load. So let me talk very briefly about why that is, right? So who knows what parts are part of an air conditioner? So you have like a compressor and a blower, pump, all that kind of good stuff, right? All of those are effectively just small motors that are moving refrigerant from one point in a system to another point in the system and managing the pressure inside the system and all of that kind of good stuff. Well, the compressor is typically a three-phase motor, but the blower fan is typically a single-phase motor, which means it's going to be connected across only one set of these phases, right? So that means that you're going to have an unbalanced system. So if you were building a system that had multiple HVAC units, you would want to connect like one of the blower fans between the A and B phases or between the A and B terminals here, another one between the B and C, a third one between the C and A, so that overall things get as close to balance as possible. So even if you're dealing with an unbalanced impedance, because that's what you were given, if you get to implement multiple ones of them, you can balance things out by swapping the phases on the single phase portion of that load. It's a very, very common practice. You get to go physically go out there and wire it. It'll be on the drawings and all that kind of good stuff as well. Okay. So the overwhelming majority of cases that you're going to face, even in an industrial practical setting, you'll be able to look at systems as if they were a balanced three-phase load. And if it's imbalanced, you're going to try to imbalance it as much as possible so that it behaves as close to a balanced system as you can get it, because that makes the math much, much easier. Okay. All right, so I want to illustrate what the benefits of having a balanced system are to you guys. And so in order to figure that out, what we are going to do is we are going to mathematically determine what our line currents are in this system. So earlier, I defined line currents, I say earlier Tuesday, I defined line currents to be the currents flowing through the transmission lines. So I'm just going to label them on this figure. So our line currents are going to be IAA, the current flowing through the A phase of the transmission line. IBB, the current flowing through the B phase of the transmission line. ICC, the current flowing through the C phase of the transmission line. And I'm doing this in a different color because it's not commonly considered a line current, but we're going to need it, is INN, the current flowing through our neutral conductor. So we are going to make an assumption here. We are going to assume that our source side neutral is our reference terminal for our analysis here. So I want to be very, very clear about this. It is likely the case that the neutral conductor on the source side is going to be tied to ground in a physical system, but it is not required. We are making this assumption here purely for math purposes, not for any practical purposes. Okay. So if I were to write a Kirchhoff's current law equation for the neutral conductor on the right-hand side of my circuit, or the neutral node on the right-hand side of my circuit, I'm just going to have that line current IAA plus that line current IBB plus that line current ICC plus that neutral current all add together and come to zero, because Kirchhoff's current law says all of the currents entering a node have to sum together and make zero. So let's do the math down here. We have IAA plus IBB plus ICC plus INN is equal to zero. And now what I'm going to do is I'm going to use Ohm's law to rewrite all four of those currents in terms of these impedances. Okay, so let's think about this really quickly. So if I want to express the current IAA in terms of these impedances, I need to know what the voltage drop across those impedances is going to be. Okay? So using Kirchhoff's voltage law, we could say that the voltage drop from here to here is what we're interested in, right? So I have VAN minus let me write this correctly, capital N to lowercase n. Anybody confused as to where that's coming from? All right, so effectively I'm writing the KVL equation. I'm starting from here. And go all the way around. Like this, actually. I'm going to start it from right here, because this is all the neutral. Okay. So I have negative VAN plus the voltage drop across those impedances, plus the voltage drop from this guy to this guy. That's what V capital N lowercase n literally means. Positive polarity is here, negative polarity is here. And I've completed my path. So the voltage drop across those series connected impedances, the line impedance and the load impedance, is simply VAN minus V capital N lowercase n, according to Kirchhoff's voltage law around that loop. I could write a similar loop for the B phase and a similar loop for the C phase. And so what I'm going to come up with is V lowercase a n minus V capital N lowercase n divided by ZWA plus ZYA plus V lowercase b n minus V capital N lowercase n over ZWB plus ZYB plus the CN minus V capital N lowercase n divided by ZWC plus ZYC. And then I need the current flowing through my neutral conductor. So that's just going to be negative V capital NN divided by ZN. Let me make sure I'm using the right notation here. Yes. Okay. Is equal to 0. All I've done here, to be clear, is apply Ohm's law, and I found the voltage drop. Sorry, this is scrolling wildly. I found the voltage drop across my series impedance ZWA plus ZYA by doing a KVL equation around effectively the outside loop that contains that neutral path. Then did a similar KVL to get the voltage drop across the B phase impedances, a similar KVL to find the voltage drop across the C phase impedances, and then I'm just using Ohm's law. The reason why this last term has a minus sign instead of a plus sign is because the current is flowing from the lowercase n to the capital N, but we have been using the voltage V capital N to lowercase n. And so in order to account for that swap of polarities, I have to change the sign on that particular term. You have your hand raised. Capital B. But so all I'm doing here, the denominators of all those equations are just those two impedances in series. So the denominator of the VAN minus V capital NN term is just ZWA plus ZYA. The denominator of the second term, which is for the B phase, is CWB plus ZYB. The denominator for the C phase portion is ZWC plus ZYC. I'm using capital letters for all of those things just because I use capital letters here, but it really doesn't matter as long as you understand that it's just those two impedances in series. That's all it is. We're just trying to find what those currents are through those impedances so that we can add them together and set them equal to 0. All right. So let me go back to our equation here. So if our network or circuit is balanced, this equation reduces to, so just as a reminder, our criterion for having a balanced network, in particular here, we're going to be looking at these impedances, is that all of our transmission line impedances are the same thing, and all of our load impedances are the same thing. So I'm simply going to replace ZWA, ZWB, and ZWC with ZW, ZYA, ZYB, and ZYC with just ZY. So if I move the VNN over ZN term to the left-hand side of the equal sign, I'm going to have VAN minus VNN over ZW plus ZY. VBN minus VNN over ZW plus ZY. And VCN minus VNN over ZW plus ZY. So when I have a balanced system, all of those impedances are the same, so I can just drop the subscript, all right? Now what I'm going to do is I'm going to move all of those VNN terms from the right-hand side over to the left-hand side, all right? So we're going to have VNN divided by ZN. Excuse me, this should be capital. Plus 3 VNN over ZW plus ZY, because that term shows up 3 times when I move it over. I'm just going to multiply it by 3 to consolidate things, is going to be equal to VAN plus VBN plus VCN divided by ZW plus ZY. One more algebraic step here. I'm going to factor out that term of VNN so that I have 1 over ZN plus 3 over ZW plus ZY is equal to VAN plus VBN plus VCN divided by ZW plus ZY. Everybody okay with the algebra that I've done? Hopefully nothing too wild or crazy. All right, so to this point, we've only considered what the implications are if our transmission line impedance is the same and our load impedance is the same. Now let's consider what shakes out when we have a balanced 3-phase source, which we should always have. Okay? So I mentioned earlier that VBN, let's scroll back up here so we can see exactly what I'm talking about. For a balanced 3-phase system, VBN is simply VAN multiplied by a factor of 1 angle negative 120 degrees. And VCN is simply VAN multiplied by a factor of 1 angle negative 240 degrees. So I'm going to put that relationship in right here. So I'm going to have VAN multiplied by 1 for the A phase plus 1 angle negative 120 degrees for the B phase plus 1 angle negative 240 degrees for the C phase, all divided by ZW plus ZY. So one of you guys take your calculator and tell me what 1 plus 1 angle negative 120 plus 1 angle negative 240 is. 12? Do the math. Zero. When I add these three voltages together, comes out to be zero. So I have VAN times zero over ZW plus ZY. So what's the right-hand side of this equation look like? Well, anything times zero is zero, right? So I know that VNN times 1 over the neutral impedance plus 3 over the series combination of the transmission line impedance with the load impedance is equal to 0. What does this imply? If none of those impedances are 0, the voltage drop across my neutral conductor has to be 0. So if the voltage drop across my neutral conductor is 0, what does that mean about the current flowing through my neutral conductor? It has to be 0 as well. So this is pretty interesting, actually. Because our neutral conductor in this system has a 0-volt drop across it, but also no current flowing through it. So it's behaving as if it's both a short circuit and an open circuit at the same time. What that means is that in a balanced three-phase system, the neutral conductor is completely and utterly unnecessary. It doesn't do anything except cost money to install, right? It's used because not all systems are perfectly balanced, but what we're going to find is that it just carries a very, very small amount of current. All of the imbalance is going to be carried in the neutral conductor. And so that's why it can be sized significantly smaller than our transmission line cables, because it doesn't have to carry as much current. So that's literally the reason why it has a different set of specifications in the electrical code. All right, so putting in these results, we can now take another look at our line currents here, right? So IAA was VAN minus VNN over ZWA plus ZYA for a balanced system. This is simply VAN over ZW plus ZY. IBB was VBN minus VNN over ZWB plus ZYB. In a balanced system, this becomes VBN divided by ZW plus ZY, which could be expressed as VAN over ZW plus ZY times one angle negative 120 degrees because of the relationship between VAN and VBN, or simply IAA times one angle negative 120 degrees. So that means that in a balanced three-phase system, the line currents have that same 120 degrees of phase separation that we saw for our source voltage, right? And we'll get a similar result for ICC here in a moment. So in a balanced three-phase system, because the B phase lags the A phase by 120 degrees for the voltage, it turns out that the current is going to lag by 120 degrees as well. That is the beauty of a balanced three-phase system. All of our quantities are going to be related to each other by just a shift of 120 degrees. Okay. So for ICC, this is going to look like VCN minus VNN over ZWB plus, excuse me, ZWC, ZYC for a balanced system, VCN over ZW plus ZY is the same as VAN over ZW plus ZY times one angle negative 240 degrees, or IAA times one angle negative 240 degrees. So let's look at the implications of this, right? So we know that all three of our line currents have equal magnitudes, but are separated by 120 degrees. So if we come way up here, let me erase this blue line that I used to explain the KVL. And I did. So let's look at the phase currents through our load. IAN, IBN, and ICN here. How do these three quantities relate to our line currents for this system? They're the exact same thing, because those impedances are in series, and so the same current flows through both. So what that means is that our phase currents must have equal magnitudes, and they're separated from each other by 120 degrees, because our line currents have equal magnitudes and are separated from each other by 120 degrees. What if we looked at the phase currents in our source? What about them? How do they relate to our line currents? They're the negative value of the line currents because they're flowing in opposite directions. But that's not going to change their relationships, right? The magnitudes are going to be the same. And we're going to see 120 degrees of phase separation between each one. What if we wanted our phase voltages across our load? Sorry, that should be BN. If those impedances are identical, and we know that all of our currents have equal magnitudes but are shifted from each other by 120 degrees, all of those voltages should have equal magnitudes but should be shifted from each other by 120 degrees. Same thing. For our line voltages on both the source side and the load side. In a balanced three-phase system, every line current will have the same magnitude. Every phase voltage will have the same magnitude. Every line voltage will have the same magnitude. Every phase current will have the same magnitude. And everything is just shifted from each other by a factor of 120 degrees. Okay. So what that means is we can represent a three-phase YY system in a much more simple form to analyze. Okay. So that form, let's scroll down here, is what's called the single-phase equivalent circuit. So just to explain things here very, very briefly. Okay. I'm going to look at the A phase here. So there's my source terminal for my A phase. Here's the neutral terminal for my A phase. Here's my voltage VAN. Here's the capital A terminals for my load side. So here is my transmission line impedance ZW. Here's my load impedance ZY. And then here is where I have to make a caveat here. It's not really a caveat. Earlier, we observed that there was no current flowing through the neutral terminal and there was no voltage drop across the neutral terminal, which means that we can simply put a wire here, regardless of what the actual impedance of our neutral conductor is, without changing anything whatsoever. So it does not matter what the impedance of the neutral conductor is. In our single phase equivalent circuit, we are just going to short the neutral on the source side to the neutral on the ground side. We could have, so this is our A phase equivalent circuit. Our B phase equivalent circuit is going to be literally the same thing, except we're going to use the subscript B. And over here, we will have our C phase equivalent circuit. Capital C. Like so. So let's talk very briefly about what quantities that we can solve for using these equivalent circuits. So I believe wholeheartedly that we should be able to solve for the phase voltages across our load. The phase current through our load. The phase current through our source. and our line currents using these single phase equivalent circuits. These are the four quantities that we can solve for directly. Okay. Now, I would argue that we never need to actually draw or analyze the B phase equivalent circuit or the C phase equivalent circuit. Somebody tell me why. Because they're the same exact thing. So if we want the B phase, we just solve for the A phase quantity and subtract 120 degrees. If we want a C phase quantity, we solve for the A phase quantity and subtract 240 degrees. There is literally no reason whatsoever to keep doing the same dumb math over and over and over again when we can get the exact same result just by shifting it to the B phase or the C phase. Because in a balanced three-phase system, we know that all of these magnitudes are the same damn thing, okay, across each phase. All right, so I'm going to pass around the in-class assignment, and we're going to work it together. We're going to work it together so I can explain to you how and why. How to solve outside of these. So I'm going to open up the in-class assignment here on my tablet. Here we go. So we're once again back in the world of word problems, which I understand that you guys hate, but we're going to be using the same equivalent circuit for literally everything. So I don't feel the need to draw it over and over and over again. All right. So in this first problem, we're told that we have a positive phase sequence, balanced three-phase Y-connected source with a phase voltage of 120 volt RMS magnitude, is supplying power to a balanced Y-connected load with a per phase impedance of ZY is equal to 40 plus J10. We want to determine the line currents if the angle for the voltage VAN is equal to 0 degrees. So just for you guys' benefit, I'm going to draw this circuit out. So we have a Y-connected source. Over here, we have a Y-connected load. Well, this A, B, C, capital A, capital B, capital C. Nowhere whatsoever is it mentioned that our transmission lines connecting these things have any impedance, so I'm just going to draw a short circuit. Unless you're told what the transmission line impedance is, assume it's 0. Okay. So this is our circuit. From the problem statement information, we know that our voltage VAN has a magnitude of 120 and an angle of 0 degrees. We know that our impedance ZY has a value of 40 plus J10. and we're trying to solve for our line currents. So our line currents in this system is going to be IAA, IBB, and ICC. While we're at it, I'll just draw them on the figure as well. Like so. So what we're going to do now is we're going to use our single phase equivalent circuit to solve for the quantities indicated. So our A phase equivalent circuit is going to be 120 angle 0 degrees volts RMS. For our source, our impedance ZY has a value of 40 plus J10 ohms. And we want to solve for our line current IAA. How are we going to do it? Voltage divided by impedance. Full stop. 120 angle 0 volts RMS divided by 40 plus J10. .910 angle negative 14.036 degrees. Amps RMS. Congratulations, you guys have just analyzed a three-phase circuit. It doesn't have to be difficult. I know it looks wildly complicated, but for every YY system, you can literally break it down into a simple equivalent circuit like this that you guys have been able to analyze for weeks at this point. Okay, so we found IAA. How do we find IBB? Subtract 120 degrees. No other math whatsoever. So 2.910 with an angle of negative 134.036 degrees. And ICC will be 2.910 with an angle of negative 254.036 degrees. If my mental math is correct of subtracting 120, looks like it is. Now, this was a pretty trivial circuit, but we have analyzed it nonetheless using that single phase equivalent circuit. So any questions about this? All right, so let's take a crack at problem 2. So we have positive phase sequence, balanced three-phase Y connected source with a phase voltage of VAN is equal to 230 angle 0 degrees volts RMS that is supplying power to 2 Y connected loads in parallel. Just as a heads up, the only way that you can combine loads in a three-phase system is in parallel. Like there physically isn't a way to make a series connection. All right. The loads have impedances of ZY1 is equal to 15 plus J8 ohms, and ZY2 is equal to 12 minus J5 ohms. Transmission line connecting the source to the loads has an impedance of ZY is equal to 0.3 plus J 0.05 ohms. We want to determine the phase currents in each of the parallel loads. So just for you guys' sake, honestly, after you do a couple of these, You really don't need to draw the circuits anymore. Or at least the three-phase circuit. This is what it would look like. So here's VAN, VBN. Down here will be VCN. I have two loads in parallel. So I need to draw that box better. ZY1 in parallel with ZY2. ZY1 in parallel with ZY2. ZY1 parallel with ZY2. Just going to tie all those together. So this is my load side neutral, capital A, capital B, capital C, lowercase a, lowercase b, lowercase c, lowercase n. Transmission line, ZW. W. CW. From our problem, we know that VAN is 230 angle 0 degrees volts. ZY1 is 15 plus J8 ohms. ZY2 is 12 minus J5 ohms. ZW is 0.3 plus J 0.05 ohms. Now we need to draw our single phase equivalent circuit. So I am happy to invite literally any of you guys to come up here and draw the damn thing. Take a crack at it. All right, so Garrett's going to be taking over the helm here for a moment. On the tablet. Why? Okay. If you make a mistake, I'll correct you. Not a big deal. Yeah. I ain't never done this before. Gotta do a thing. I get it like this. Get there. A little tiny. Okay. They're all the same. Yeah. Great. Wonderful. Perfect job. All right. So, anybody have a problem with this single phase equivalent circuit? Because it looks absolutely correct to me, right? It is exactly what we would expect if we had two Y connected loads in parallel and we're looking at it on a per phase basis. So what are we solving for? What does the problem statement tell us that we're solving for? Our phase currents, right? So that's going to be this current. Let me put it on the other side here. IAN1. And this current IAN2. Just for the sake of argument, I'm going to label things lowercase a, lowercase n, capital A, capital N, so it's a little bit more obvious why we're calling it IAN1 and IAN2. Okay. So, how am I going to solve for those currents? Okay, so if we can find the voltage VAN, we can solve for either of them, right? So let me just label this voltage right here. So the suggestion from Preston is to solve for that voltage VAN and then use Ohm's law to find both those currents. That's exactly how I did it when I wrote this morning. So how are we going to solve for that voltage? Okay, so I'm going to find the equivalent impedance. That works for me. So let's call this ZYEQ. So that's just going to be 15 plus J8 times 12 minus J5 over 15 plus J8 plus 12 minus J5. All right. And then what did you suggest doing after that? Okay, so you are, just to be clear here, solving for the line current. Okay. So Preston is suggesting that our line current IAA is going to be our voltage VAN divided by ZW plus ZEQ, ZYEQ. Then he is suggesting that the voltage VAN is equal to our line current IAA times the impedance ZYEQ. And then from there is saying that IAN is, excuse me, IAN1 is simply VAN over ZY1, and IAN2 is going to be VAN over ZY2. Okay, so I want to start off by saying there's literally nothing wrong with what you have suggested here, but geez Louise, there's a lot of steps. Okay, nothing wrong with it, but let's talk about how we could do it a little bit different. Okay? So to me, I solved for the quantity VAN using voltage division because I have two impedances in series once I have that equivalent impedance, right? So that would get us from here down to here without ever solving for the current, right? But just as an alternative thing here, if you really wanted to solve for the current, you could then use current division to solve for either of those phase currents directly, right? There's always 5 or 6 ways to work one of these, right? So I want to be very clear here. There's no problem whatsoever with the method that Preston has suggested. It logically makes sense. Calculations and all that kind of stuff will make sense. It is just slightly less efficient than using a different method. Nothing wrong with it. Everything logically makes sense. And if that's what he's comfortable with, I am fine with that. I just want to make you guys aware that you can use literally all of the little tips and tricks and all that kind of stuff that we developed when we were analyzing single phase circuits to these 3-phase circuits, because we're using a single phase equivalent, right? So current division, voltage division, KCL, KVL, all that kind of jazz can be used in this analysis to make the calculations take less steps and all that kind of stuff. But let's follow through with what Preston suggested. All right. So if I take 15 plus 8I times 12 minus 5I divided by 15 plus 8I plus 12 minus 5I. I get the equivalent impedance to be 8.134 minus J 0.126 ohms. I'm going to store that in my calculator as X. So to solve for IAA, I'm going to take my voltage VAN, which if I'm not mistaken is 230 angle 0 degrees. And I'm going to divide that by ZW 0.3 plus 0.05I plus what I stored in my calculator is X. And I get, let me do this in polar form because it's a current, 27.269 with an angle of 0.516 degrees. Amps. My voltage VAN is simply that current times the equivalent impedance, which I have stored in my calculator as X, which I get to be 221.837 angle negative 0.371 degrees volts RMS. I'm going to store that in my calculator as Y. And so to solve for IAN1, I'm just going to do Y divided by 15 plus 8I. $13.049 with an angle of negative 28.444. Amps RMS. And to solve for IAN2, the variable that I have stored in my calculator as Y divided by 12 minus 5I. I get to be 17.064 with an angle of 22.249 degrees. Yes. Everybody else getting similar results? If I'm not mistaken, those are correct. So in order to solve for the phase currents in the B phase, what would I do? Subtract 120 degrees. For the C phase, subtract 240. Absolutely right. Not going to bother doing it here. You guys are catching what I'm throwing. So before we move on to the final problem in this in-class assignment, anybody have any questions, comments, or concerns about anything that we did here? Right. Just giving you a fair warning on this next problem, I have thrown you a slight curveball. So we still have a YY system. I give you the line current, I give you the line impedance, But I give you a line voltage as well, right? So I give you the voltage VAB. So let's draw things out here really quickly. So here is VAN. VBN. VCN. Here is the voltage VAB that you were provided. Have ZW. A, B, C, lowercase n. A, B, C. And we are asked to determine what our load impedance per phase is. So we're solving for ZY. And we are given our line current IAA. So let's write down our givens here really quickly. IAA is 16.78, angle 20.98 degrees. Amps. VW is 1.2 plus J 1.8. And VAB is 440, angle 70 degrees, volts RMS. So why this is a bit of a curveball is because we have to do a little bit of work to figure out what to put into our single phase equivalent circuit. So let me explain what I mean here, right? So in our single phase equivalent circuit, we put the voltage VAN as our voltage source. Here's ZW, which we know. Here's ZY, which we're trying to find. Like so. We were given IAA. So I'm just going to put question mark here and a question mark there because those are the two things that we need to figure out effectively, right? So probably the most important thing for us to figure out is that voltage VAN. Okay? In order for us to figure out that voltage VAN, we need to look for a relationship that is going to relate it to that given voltage VAB. So what I'm going to do is I'm going to write the Kirchhoff's voltage law equation around this path. Okay. So I have negative VAN because I hit the negative polarity terminal first, plus VAB plus VBN is equal to 0, or VAB is equal to VAN minus VBN. Everybody okay with that KVL equation and the algebra? That's fine. So it looks like I have a problem here. Because I have one equation and two unknowns. Right? I don't know what VAN is, and I don't know what VBN is. But I do know that VAN and VBN are related to each other, right? So I could write this as VAN times 1 minus 1 angle negative 120 degrees. Somebody tell me what 1 minus 1 angle negative 120 degrees is. I'm sorry, what was that? Right, but I'm asking, so if you put in your calculator the number 1 minus 1 angle negative 120 degrees, what are you going to get back? Square root of 3 angle 30 degrees. That's a very important quantity that you're going to use a lot when we're dealing with three-phase systems, right? So this is the same thing as VAN times √3 angle 30 degrees. And from here, we can see that VAN is simply VAB divided by √3 angle 30 degrees. So what we've accidentally stumbled on here, accidentally on purpose, to be honest, is a means by which to convert from phase voltages to line voltages for a Y-connected source, right? So it's always going to work this way. If we are given a phase voltage and we need the line voltage, we multiply by √3 angle 30 degrees. If we're given the line voltage and we need the phase voltage, we divide by √3 angle 30 degrees. That's how it's going to work literally every time. So you'll never see me derive it again. It's a simple conversion fact, okay? So from here, substituting in our numbers, so that's going to be, I believe, I said it was 440 angle 70. Thank you. $254.034 angle 40 degrees volts RMS. So this is a known quantity now. 254. All right. So we've got one big question mark taken care of. So how are we going to figure out the impedance? Because that's actually the thing that we're looking for now. So let me rephrase what Preston just suggested, right? So our impedance ZY is going to be the voltage VAN divided by the current IAN, because that's literally the definition of impedance, simply the ratio of the voltage drop across the element divided by the current flowing through the element. Now, we can see that IAN is the exact same thing as IAA, our line current, because our transmission line is connected in series to our load impedance, right? How are we going to get that voltage VAN? So to use a voltage divider, though, we would have to know what ZY is. Any other thoughts? You've nailed it. 100% correct. So VAN minus IAA times ZW, because all this quantity right here is VAN using Kirchhoff's voltage law around that single loop. Knocked it out of the park. So we now know all of these quantities. So we can simply plug it in, right? So that's going to look like 254.034 angle 40 degrees volts RMS minus IAA was 16.78 angle 20.98 degrees. Amps RMS multiplied by ZW, which was 1.2 plus J 1.8. Divided by our current IAA, 16.78 angle 20.98 degrees. Amps RMS. All right, so I'm going to be a little bit lazy here. 16.78 angle 20.98. I'm going to store that as Y so that I'm going to have X minus Y times 1.2 plus 1.8 I over Y. I get 0.22230 minus J 1.307 or 1.327 angle negative 80.040 degrees. Oh, let's just check things here really quick. Oh, really different number. What did I make a mistake on? So the little an divided by our line, let's talk about that right quickly. Yeah, I'm gonna scratch this out. I probably put something in the calculator else. So what was just suggested was that we take VAN divided by IAN, right? Well, that, from looking at this thing, is actually going to be ZW plus ZY. So we could subtract. Yep, absolutely. So VAN over IAA minus ZW is equal to ZY. So let me throw that in my calculator and just see, make sure I have stuff stored correctly. That's probably what the issue is. Process is right. Me just hitting a number wrong. So 254, blah, blah, blah. That seems correct. Oh, there we go. So I did 168 angle 20 instead of 16.78 angle 20. That makes sense. 16.78 angle 20 for 20.98. For that as y, x divided by y minus 1.2 plus 1.8 pi 13.482 angle 13.441. These ohms should be the same thing either way. There we go. All right. Okay, so that's enough out of me for today, and we only have 7 minutes left anyway. I hope you guys have a great Easter break and all that kind of good stuff. I'm going to put a homework assignment up today. It'll be 3 problems, and it'll be due well after you get back. So you shouldn't have anything to worry about over the break.